Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT Bombay. So we are into the last legs of this course, and we are in the middle of week number 11. So, in the background, what you see now is a bunch of different kinds of applications that adaptive control has found using. These are things like, drones, uh, fighter aircraft, spacecrafts, neural nets. So, so this is sort of the applications, or at least one set of applications that I'm hoping that the algorithms that you've learned in this course will help you work with. I'm of course always fascinated by newer applications. I've seen quite a bit of automobile system applications also, and I am always open ears to know what you're working on. Yeah, so please ping me and let me know what sort of things that you are using these adaptive control ideas for. Um, and I can say for sure it will be very interesting for me to learn. Now, what we are doing since the beginning of this week is the initial excitation based adaptive control. So we already know, um, the standard adaptive control for parameter learning requires the knowledge, requires persistence of excitation. Yeah, we already know this is more like an a condition on identification and not something, or in fact something that precedes adaptive control itself, and not something that can be easily gotten rid of. So, in order to make it a little bit more realistic, several researchers worked on trying to relax this condition. And one such relaxation is what we are looking at right now. And this is based on using only initial excitation instead of persistent excitation. So, the idea being that only for an initial phase of time, you have sufficient excitation, and beyond that, you don't, right? And so the question is then, can you still, achieve your, parameter convergence and parameter learning in those cases, right? So this is the general idea. Now, we started with looking at a single integrator system, right? Um, and this was rather interesting, I hope. We don't write it as a differential equation, but we write it in this regressor parameter form, and and then we go on to look at development of these multiple layers of filters, right? So we have two filter layers here, right? So we have one filter layer, which is the YF. We talk about the implementability of this filter, and then we connect the filtered variables also, just like we have a connection between the standard, the original variables y and u, and of course then finally we design a second filter layer. Once we did the second filter layer design, we then started to address the tracking problem. Until that point, we didn't even really care about the tracking question itself, right? So we of course designed this parameter update without any Lyapunov analysis at this point, because we are rather comfortable with the fact that there is nice negative terms appearing here, yeah, which is unlike what you get in standard adaptive control loss. Now, once you have this sort of a situation, we then choose our control also. So the control law is also already chosen, and so all we are left with now is to do the analysis. This, of course, we remember is reminiscent of the other non-certainty equivalence method we looked at, which was in connection with parameter projection. Yeah. So I hope you can connect these dots sort of. Yeah. So we do the analysis. We of course have this dummy variable lambda which we use to dominate things. Again, similar to what we had earlier. And finally, we said that if there is this initial excitation condition, which was of course much weaker than the persistent excitation condition, we can show negative definiteness, right? So we had these rather nice properties, right? I mean, then and whenever you see something nice, uh, I hope just like I do, I try to critique it. Right? I try to figure out where the issues are or what is good, what is bad. Yeah, not just bad. I mean, of course, there's a very very powerful method. I've advocated it myself, and I strongly recommend that you look at these authors' other works, because although there are other composite adaptive controllers which use similar ideas, in my opinion, these authors seem to have done it in a rather simple, intuitive way. Yeah. All right. So of course, we said that you don't have to verify the initial excitation for YF itself. It's sufficient to verify it for the original regressor Y. Yeah, great. Now, few comments were in order. So this is also what we saw. First is that if there's no excitation, robustness is still an issue. We've not handled the robustness issue. For that, you still need to do projection or sigma modifications and things like that. Yeah. Um, Second, of course, we showed how the IE condition is significantly a weaker requirement. And um, of course, we also talked about the fact that the initial excitation condition is not uniform. In fact, the condition, because the regressors typically almost always depend on the initial conditions, because it depends on the state. So, of course, it depends on the initial conditions. You need parameter dependent version of this YF. We looked at this in the integral lemma discussion a while ago when we talked about persistent excitation. But in this context, also the same idea holds. Yeah. And finally, not finally, well, we also looked at how or what would be a possible way of choosing lambdas. And we saw that this is not super easy. This is sort of a non-linear question. Yeah. The good thing for us is that such a lambda, existence of such a lambda is significantly easier to show. And we don't care about actually choosing lambda because it doesn't appear in the control law. All right. Um, the final thing we sort of mentioned and we discussed a little bit is that the behavior in the absence of excitation is not very evident. So this was one of the more key points I would say, because if you look at the update law, you see that both these terms are very excitation dependent. The first term sort of depends on uh, the YF transpose YF, so it's only semi-definite, right? So the definiteness of this, of course, is not guaranteed, and the definiteness of this is guaranteed if there is initial excitation. But if there is not, then this is also not guaranteed to be definite. So none of these are actually negative definite, right? And so uh, how will it perform, right? Because if you look at the Lyapunov analysis, this entire Lyapunov argument is based on trying to dominate this guy. Right? So you try to break this into squares and then you use this guy to dominate this. All right. So our entire argument may be in jeopardy if you don't have initial excitation. Yeah. Now what happens? How things are different in standard adaptive control is that there is neither of these two. Neither is there a negative definite term, so it's a bit sad. But there is also not a mixed term in the unknown. Yeah, because this mixed term essentially gets cancelled by using your uh, standard adaptive, right? Of course, I would say one sort easy sort of way uh, to deal with it, uh, right? One easy sort of way to deal with it. Let me see. Yeah, okay. I was just wondering about the argument, the order here. So E is, of course, so let me look at the order of things. So E is um, here is a scalar. Yeah. Z here belongs to R1 cross 2 and theta tilde belongs to R2 cross 1, right? Or R2, right? So now, one of the things that I could have done, right? If I look at the analysis here from in V dot, I would, so I'm going to put this as an aside, yeah, so that, yeah, let me draw it a little bit more straight using my tool. I'm going to use a bit of an aside. So if you look at my V dot is E dot um, minus lambda theta tilde transpose theta hat dot. All right. So now I already know what is E dot, so I substituted. So minus K squared plus EZ theta tilde is what I will get from here. And from here, I get minus lambda theta tilde transpose, and theta hat dot was all this mu f yf transpose yf theta tilde plus mu if theta tilde, sorry, I apologize, mu if yif theta tilde, and suppose I have plus some additional term mu at my disposal. All right. And if I do have this, what I can show here, right? What I can show here is that if I choose my new, let's see, if I choose my new as 1 over lambda Z transpose E, then I'm sort of fine. All right. So that's the idea. So what will happen if you make this kind of a choice of V is that if I now write this expression for V dot uh, like this, if you see, all I've done is plugged in for this V in here. And if I write this entire expression for V dot, I have this minus E squared from here, and I have the two negative terms from here, right? And subsequently, I will have this guy contributing to a term, this one, and then this mixed term comes back here. All right. Now, if you notice, we've already mentioned that all terms in V dot are scalars, so we can take as many derivatives as as many transposes as we want, and nothing changes because the transpose of a scalar is the same scalar. So you can very easily take a transpose of this guy, and E is of course a scalar, so E transpose is just E, and you will see that this transpose of this exactly matches this term. So of course these two terms cancel out, and uh, what is this nice thing that we obtain because of this is that there is no mixed term anymore. There are only non-positive terms in the V dot. Because this is non-positive, this is non-positive, and this is non-positive, right? And so there is nothing to dominate. All right. So, of course, what is the outcome of this? The theta tilde dot now has an additional term, right? And if you notice, this additional term is essentially the certainty equivalence adaptive update law. Yeah, so this is exactly what you would have done if you were not using this initial excitation based law. So the initial excitation based law now has terms in addition to what you would do in the certainty equivalence based adaptive update law. Now, what happens because of this is that suppose there is no initial excitation either. Suppose our application is unfortunately such that there is no possibility of initial excitation, forget about persistent excitation. So what happens is that these terms are then not necessarily definite, right? So these terms are not necessarily definite. Now, what that means is that you cannot really, they don't really contribute to the Lyapunov analysis. So I might as well ignore them, yeah, because they are only negative semi-definite at best, right? So what this indicates, I mean, you can choose to ignore them or you can keep them and use in the Bablat's lemma. But essentially, what you'll be able to obtain in the absence of excitation is that E goes to zero because of this term. It is, again, we don't repeat all this signal chasing analysis anymore. We've not done that for a while because I assume that all of you have seen enough of these same steps to understand which terms will actually go to zero. Yeah? So I can very easily prove that this term will go to zero in the v dot, and you can of course prove that y f theta tilde goes to zero. In fact, also y I f theta tilde goes to zero. You can prove both of these, right? So these may be some kind of attractive sets, right? Attractive invariant sets. If you remember, we talked about this attractive invariant set when we discussed this projection based adaptive control also. So similarly, you will also get some kind of an attractive invariant set in the absence of excitation. Yeah. But of course, we still end up proving that E goes to zero. And this is what we do in standard adaptive control anyway. Yeah, that we end up proving that the tracking errors go to zero. But of course, we cannot guarantee anything about the uh, parameter uh, estimation errors going to zero. So learning of the parameter is of course not guaranteed in the absence of any kind of excitation. But if you have even basic thing, something as basic as initial excitation, then you are guaranteed to have parameter convergence. But in the absence of initial excitation, things don't go bad. Yeah, you still have bounded results. That is, your E and theta tilde will be bounded because V dot is definitely semi-definite negative. And on top of it, you will also get your tracking errors to go to zero. All right. So this last point that we made last time, that behavior in the absence of excitation is not evident, this can sort of be resolved very easily by making this simple modification in the adaptive law. So this new adaptive law, as you notice, contains a mix of your uh, initial excitation based adaptation law and your uh, standard certainty equivalence adaptation law. Yeah. So I hope you understand that we can combine the power of these two methods. That is the initial excitation based law, which has these filters, and then the standard certainty equivalence adaptive controller to get the best of both worlds. Yeah, in the absence of excitation, I still get nice tracking performance and bounded parameter errors. And in the presence of initial excitation, that is some excitation for some initial time, I get parameter convergence also. All right. So this sort of last point is something we have resolved. Yeah, great. So sorry for that long initial, preamble, but it was rather essential to understand better, um, what initial excitation based adaptive laws are all about. Yeah. So whenever there is a new paradigm, it's important to, of course, understand it well, to see what are the good things it has, and then see what are the limitations also. Yeah. So what we want to do now is to look at the combination of this backstepping based ideas that we have seen before with this initial excitation based adaptive law. Now, I really hope that you remember that this initial excitation based adaptive control design did not really rely on the dynamics so much. So one would hope that the dynamics itself should not really impact the initial excitation based design. Yeah. So, but let's see how these two get combined. Yeah, that is the backstepping based ideas and the initial excitation based adaptive controllers. So, the first thing to sort of notice is that we are still going to be looking at the matched uncertainty case only. So, we are not considering the unmatched case here. So, here we have the standard double integrator with unknowns A1 and A2 and the control in the same equation. So that is the matched case. And the objective is, as usual, to drive these errors E1, E2 to 0, where E1 is x1 minus r and E2 is x2 minus r dot. All right. So before we, I apologize, before we go forward to doing any doing any control design, just like before we do this, we write this system in this regressor parameter form. And what we do is we only look at this system because this is the one with the uncertainty. So we don't really care about writing this in any form. So we only look at this piece of dynamics, and I'm writing this in this y theta equal to u form. So, so if I take these guys to the left, I have this y theta equal to u. As usual, I have this over parameterization here, right? Because of this additional one that I put in here, right? And that's it. So, and then y is of course x2 dot and minus x1 and minus x2. It's like that way. Right? Now, remember that uh, as usual that uh, this guy, but I should mark it properly. This guy is not measured. Okay, so this guy is not measured. This is pretty standard, right? Because what is this? If you think of this as a mechanical system, this would be like an acceleration term, right? So usually the assumption is that only the states are measured, yeah, and not their derivatives and so on and so forth. But that's the usual assumption, yeah. Of course, you do have mechanical systems where you have accelerometers and acceleration is directly measured, but that's not very common. Okay, so so x2 dot is not measured. Remember that. So this is exactly like the single integrator case where you did have one unmeasured quantity, but we did show that even with this unmeasured quantity, you can do this integration by parts and still implement the filter. Yeah, and so that's the same here, right? So I define one layer of filters, okay, just like before, which is the yf dot is minus sigma yf plus y, and then I also define a filter on control because that's also a known quantity. So the known quantities in this equation are y and u. I define filters on both. And of course, the filter gain bandwidth is exactly the same. Right? And we take some of course that is some positive gain sigma, and initial conditions are assumed to be zero. Yeah. So so the important thing to remember is that again we are not showing it here, but these are implementable. Okay, the filters are implementable and with the same logic as before. Yeah, so there are two pieces in y. Yeah, one piece contains these two which are of course available through measurements, and then there is this guy which is not available in measurements, so we just do an integration by parts, yeah, to remove this, and that's it. And once we do integration by parts, it becomes implementable. All right, great. The other thing to remember is that just like in the previous case, nothing has changed. I mean, only the definition of y has changed. The structure of the regressor parameter form has not changed. And this is the cool thing, reason why this is sort of decoupled from the dynamics itself. So the dynamics has changed, and that change is encoded in the y itself, inside the y. But the structure y theta equal to u has not changed, right? So that's what I would say, that structure is dynamics agnostic. Yes, it doesn't really depend on the dynamics of the system. The structure is y theta equal to u. This is the standard regressor parameter form. Yeah. And because the structure is not modified, in the filtered variables, you will still have the equation uf equals y of theta. Yeah. So this still holds. Nothing has changed here. Yeah. And this is nice, right? Very cool. Okay. So those are the important points. Remember, I still write it in this regressor parameter form y theta equal to u, because of which I have uf is y of theta, and I design the filters identically, though the dynamics has changed from single, even the order of the dynamics has changed. The only thing is there is still, again similar to the previous case, of course, there is still one unmeasured quantity, but we deal with this using integration by parts, and so the filter yf is still an implementable filter. All right, excellent. Right. So now, if you sort of look at what we did in the previous example, in the case of single integrated, we add another filter layer, right? So the first filter layer helps improve performance, comes from Sloteen's original work in 80s, but it doesn't really help you alleviate the need for persistence of excitation. Yeah. So in order to do that, we need a second layer of filter, and that's what we did in the single integrator case. And in the double integrator, or if you have 100 integrators, or if you have any kind of dynamics, you would do the exact same thing. Nothing changes. So the second layer filter is of this form. YIF dot is YF transpose YF. So I think this is also this plus YF transpose YF with initial condition 0, and UIF dot is YF transpose UF with initial condition 0 again. Okay? And of course, as before, we have that YIF is positive semi-definite. Why? Because it starts at 0 value, 0 matrix now, and the derivative is a positive semi-definite matrix. Yeah, and therefore YIF dot YIF is now YIF dot is positive semi-definite. Therefore, the way YIF propagates is also becomes a positive semi-definite matrix. Yeah, excellent. Now, for UIF, also you have YF transpose US, and the structures are again chosen smartly, carefully. In what sense? In the sense that I get a similar looking filter equation, right? So the original regressor parameter form translates to the first layer filter regressor parameter form, and then to the second layer filter regressor parameter form. So the form does not change at all. Yeah, although the dynamics have changed. Yeah. So as is evident, this entire change in dynamics is encapsulated inside this quantity. Yeah, of course, also this quantity. All right. Excellent. Now, again, we choose our update law, that is theta tilde dot is minus theta cap dot, as this guy, minus mu f YF transpose UF minus YF theta hat, and minus mu IF UIF minus YIF theta hat. The update law is also exactly the same. Yeah. Remember, we are not talking about the modification that we proposed here with the certainty equivalence adaptive law added to it. We are not doing that yet. Yeah. But this is the standard initial excitation based adaptive law. Yeah. So if you do this, if you take this in this way, you know that this UF minus YF theta cap is going to be equal to YF theta tilde, and this guy by our standard regressor parameter forms in the filtered and the double filtered systems, and this becomes equal to YIF theta tilde. Okay? And once you substitute these here, you get minus mu YF transpose YF theta tilde minus mu IF YIF theta tilde. Right? And as usual, mu F and mu IF are some positive constants. Okay, so again, very standard. Oh, I'm sorry, this is already the fact that mu F and mu IF are positive is already mentioned here. I don't need to repeat it. All right, excellent. And then we of course write our usual error dynamics. Yeah, which gives me E1 dot is E2, right? And E2 dot is X2 dot minus R double dot, right? So this is A1 X1 plus A2 X2 plus U minus R double dot. So then we again write this as Z times theta. So this is where the Z shows up. You have the control and you have the R double dot. All right. So this is what you have for your dynamics. Excellent. Excellent. So what did we look at today? We sort of well, we spent a decent bit of time trying to understand trying to sort of go over the implications of initial excitation adaptive control. More specifically, we looked at a small modification to the IE adaptive controller so that you add the C, the certainty equivalence adaptive control term to it, which ensures that even in the absence of excitation, the performance of the IE adaptive controller does not deteriorate. Yeah. So that was nice. And after that, we started looking at the backstepping based extension for our initial excitation adaptive controller. So we started looking at that. And of course, we will continue on the same in the subsequent session. So I hope you're enjoying our discussion on this initial excitation based adaptive controller. And I hope to see you again in the next. Thank you.